Hey, Wheaton North, Mr. Euler here. We're going to talk about heating and cooling curves. So let's dive right in. A heating and cooling curve is a way of representing the changes of a substance. Usually it's water, but it could be any substance, as you add heat or remove heat. We'll look at adding heat first. So picture a block of ice or a couple ice cubes that are frozen. You're taking them from the freezer, right? As they add heat, as heat is added from the surroundings, what's the first thing that happens? If you were to graph it, temperature over time, as heat is being added at a constant rate, what would you expect the graph to look like? Well, this is before it starts melting. So you just took it out of the freezing cold freezer. Think the deep freezer. Right? It's way colder than even the freezing point. So first it would have to rise in temperature. It'd be a solid, and it would be rising in temperature, right? It would get up to where the point at which it starts melting, and then only then would it start melting, right? So the next part, it would start melting, and as it melts, it actually stays cold. You know this from a glass of water, right? If you come back to a glass of water and there's been ice in it, the water, even when the ice is really, really small, it's been melting this whole time, the water is still very cold, right? The water stays cold as long as there's ice in it because the ice is cold, right? While the ice is gaining energy, it's melting, and the temperature actually doesn't change while that's happening. So the graph would flatten out because now you don't have a change in temperature. If heat continues to be added, once it's all melted, then it will start rising in temperature, right? And so you'll start to see a temperature change again, and the temperature will go up over time. If you continue to heat it, if it continues to gain energy, eventually you'll get to the point at which it starts vaporizing really quickly, right? We would call that boiling. And so you could use the term vaporization here, or vaporizing, or boiling. At this point, we've talked about how the molecules are leaving the liquid phase, and energy is being absorbed by the breaking of those IMFs, right? So again, we reach a plateau where it flattens out. So notice where you're actually doing a phase change from solid to liquid in the melting, or from liquid to gas, the temperature is actually flat. It doesn't change while that's happening. Now we can attach some equations to this. We've already done Q equals mc delta T. And so that works when you have a temperature change. As your solid is increasing in temperature, your mass times your specific heat times your change in temperature would give you the heat that's required to do that change, right? Your C depends on the phase that you're in. So there's a different C value for solid water or ice as liquid water, right? So you have to make sure you're going to be using the right one. So here it would be 2.09. Once we get up to the melting phase, there is no temperature change. If you were to try to do a temperature change, it'd be 0, and then the whole thing would be 0, right? But it's not true that it's not absorbing any heat. It is absorbing heat. And so we have a different equation for when you're on a plateau because there's no temperature change. It's the mass times the heat of fusion in this case. The heat of fusion is a scientific word for freezing, essentially. And so that term is used when you're on that plateau, whether you're freezing or melting. So Q equals M times HF, your heat of fusion is, notice the units are joules per gram because you're taking it times a mass, which is grams, and so that will just give you joules, right? It's how much energy for every gram is required to convert that substance from solid to liquid. Once you start going up the liquid slope again, then you're using Q equals mc delta T again, right? Because you have a temperature change. Then once you get to the next plateau, again, there's no temperature change, so you have to use an M times HV or HF formula, right? The difference between HV and HF is that it takes a different amount of energy to break the IMFs completely. And this is called the heat of vaporization. So notice how much bigger this is. It's 2259 for water, whereas it's only 335 to melt it, right? Now, if we were to keep going and continue heating it, you would get another slope again, right? So the melting point is at 0 degrees for water, and the vaporization or the boiling point is at 100 degrees. Notice that those plateaus exist at the melting point and the boiling point, right? If we continue to heat it, you would see a temperature change again, right? And so there's a fifth section of the graph. Sometimes we refer to these with numbers: section 1, section 2, section 3, section 4, and section 5. You want to, if you haven't yet, pause the video here and make sure you have all this written out. Give yourself some space because we're going to be adding more stuff to this as we go. but you want to draw out this heating and cooling curve graph, okay? Now, all of this is considered endothermic because we're adding heat, right? We're going up the graph. You can also go down the graph. This would be called exothermic because you're losing heat. Heat is being lost. So picture ourselves going back down. If we go from gas and then we reach that boiling point again, or it could be considered the condensation point, you would condense the gas into a liquid, right? This is what happens when it rains. The gas cools and then converts into liquid, and then it will fall down on the earth as rain. If you were to continue to lose heat and cool the sample, then it would go down it would cool as a liquid, and then when you get to the freezing point, it freezes. So in the forward direction, it's melting, but in the reverse direction, it's freezing, right? This occurs actually at the same temperature, at 0 and 100 degrees, right? Now we could also look at an example where we don't have water. Here I have the data for mercury. Notice its melting point is negative 39. And so what happens with mercury is you increase in temperature, and then you plateau at your melting point, but your melting point's not at 0 anymore, right? Because 0 is just the melting point for water. Mercury melts at negative 39 degrees, right? So my plateau is occurring below 0 degrees. And then you have it all melted. It would rise in temperature. Notice how steep I made that slope. That's because we have a pretty low specific heat, so it would gain temperature. It would increase in temperature really quickly. And then you get to your boiling point. But notice your boiling point's not at 100 like it is for water. Your boiling point's at 357. So your plateau would be much above that 100-degree mark, right? And then you'd have the gas phase also after it's been boiled. So to summarize, if you're on a slope, you want to use Q equals MC delta T, right? This would be sections 1, 3, and 5 of the graph, right? If you want to use the numbers to refer to them. If you're on a plateau, it's either M times HF if it's the first plateau, or M times HV if it's the second plateau. You have to pick the right number based on the scenario, right? If you're fusing or freezing, then you want to use the heat of fusion. If you're vaporizing or condensing, then you want to use the heat of vaporization. One other thing to note with going backwards in the exothermic direction, these values would be negative because you'd be losing that heat, right? So what we typically do is we'll just make this value negative. We'll just use negative 289 to indicate that we're losing 289 joules for every gram rather than gaining it. The negative just indicates direction. So you can also keep everything positive and then just make it negative at the end to indicate that we're losing this much energy rather than gaining it. That's the idea behind the heating and cooling curve. We'll do more practice, and we'll have another video where we go through some examples where you actually do the calculations, but I wanted to have a video just to kind of go through the process and go through the concept of it and show you kind of why we have different equations for the different sections of the graph. All right, this is Mr. Euler signing out.